In our study of equilibrium, we have now had the opportunity to look at a couple of things like to what extent does a reaction proceed in the forward direction? In other words, to what extent do we go from the reactant side over to the product side? Now, what we have seen is that a lot of systems, a lot of reactions, a lot of processes that occur in nature don't actually go 100% to completion. They'll go to an extent, right? So we've seen that certain reactions will have an equilibrium constant. We've noticed that with acids and bases, we have a bunch of acids and bases that don't ionize completely. They ionize, again, to an extent. So the last section that we want to kind of look at in this idea of equilibrium is something known as solubility product equilibrium, what we have over here, okay? And solubility product equilibrium, fancy term, but in essence, it comes down to this question. Why do some ionic compounds break up completely in water and others don't? So recall, we talked about the solubility of substances way back at the beginning of the year, right? One of the first episodes we ever did was on this idea of, which are the substances that break up in water, which are the substances that stay together. And so we learned back then, and I kind of lied to you, but we learned back then that what we saw was that certain substances are considered to be soluble, in other words, that they disassociate, while others, the ones that we called box 4, we said that these guys never, ever, ever disassociate. They don't break up. Well, we lied. Why do I say I lied? Because what we find is that even things that are insoluble will, here's the phrase, to an extent break up. And so what we need to figure out then is, well, what do you mean by to an extent? And so in order to help us understand this idea, what we want to do is let's take a look at over here our equation where we're going to take lead 2 iodide and we're going to put it into water. Now here is the typical trap. When I put lead 2 iodide into water, the idea, or what you should immediately think of, is that lead is one of our fat bastards. This thing fell under box number 2, which was the halides, and the halides were always insoluble when they were bonded with lead and mercury and silver, etc., etc. And what we should take away from this is that my expectation going in is that lead 2 iodide will be insoluble. It will not be able to break apart and form lead ions or iodide ions like we're seeing over here on this equation. But check out the video below. And what you'll notice is that in this video, as I place some lead nitrate in combination with potassium iodide, is that we see immediately some of the lead iodide get produced. Right? So you see this very distinctive and very clear yellow precipitate start to form. But as we stir it, we notice that it disassociates, it dissolves. So we add a little bit more, right? And then we add a little bit more. You notice that now it takes a little bit more work and we're stirring it more and more and more, but eventually it too disassociates. And so you're going to keep adding until at a certain point you're going to notice it's going to be very difficult for the lead iodide to break apart. And so at that point we say, okay, look, lead iodide is insoluble. But what happened all those times before? What happened in all of those instances where it kept disassociating, where it kept breaking apart? And so a common question then is, well, how is the insoluble salt able to do this? And the answer has to do with, notice right over here, what the value of our KSP, or our equilibrium solubility product constant, is going to be. And what I see here is that this KSP is itty bitty, teeny weeny. So that means that this is not a reaction that heavily favors the formation of products. Quite the contrary. I expect that most of the time this reaction is going to stay on the reactant side. It's gonna stay as the PbI2 solid. But given that it does achieve an equilibrium, as long as I keep the concentrations of lead ion really teeny tiny and the concentrations of iodide ion really, really tiny, then this is a substance that will disassociate. This is a salt, an insoluble salt, that can break apart. It's just terrible at breaking apart. It sucks at breaking apart. Thus, why we see such a teeny tiny K equilibrium constant. So what does this idea of KSP tell us? Well, it tells us that in a nutshell, we can disassociate, we can take an insoluble salt and under certain circumstances actually break it up. But what this also will give us some insight to is that it is possible then to have something like lead ions in a water supply. And that, as you can already imagine, is probably a terrible idea. So you may have heard sometimes that, a water supply is poisoned, or that there's a high concentration of lead ion or mercury ion in the water. And you might be asking yourself, well, how exactly does that happen? And the answer is that if we don't have anions, so if we don't have certain things like iodide or fluoride or carbonates or other anions in the water to help precipitate or crash those metallic ions out, if we don't remove them from the water supply, then it is possible to have very heavy metals floating in a water supply or floating in a water solution. So how much do we need to add of an anion? How much do we need to ensure that we add to the water to make sure that no heavy metal is left floating around? And well, it's going to depend on what's the reaction in question. Why do I phrase it that way? Well, let's take a look and let's actually determine the solubility of lead 2 iodide in water. And so we're going to approach this just like we have every other icebox. We're going to tackle it the same exact way. We're going to need to start off by first writing our equilibrium expression. So in this case, my equilibrium expression is going to be that the KSP is going to equal the concentration of my products over my reactants. But, and this is the first critical piece of awareness you want to have, when we look at solids and their ability to disassociate, what we're going to notice is that because it's a solid, it will not enter into the equilibrium expression. So in this case, what we're going to find is that the KSP is simply going to be the concentration of Pb2 plus at equilibrium times the concentration of the iodide ion at equilibrium. Now remember, this is going to be squared. So something to realize is that while our denominators have now disappeared, we will be looking at higher order math problems because oftentimes you're going to be dealing with coefficients in these substances as they disassociate. So don't be afraid of seeing x cubed or x to the 4th or x to the 5th. So with my equilibrium expression in hand, we can go back over here to our equation, and what I'm going to start off is say, okay, lead 2 iodide will to an extent break up in water. How much does it break up? So since I don't know, that means I can assume initially we had pure water, so there was none of the lead ion, none of the iodide ion in solution. Now, as some of it broke up, we don't know to what extent, so this is going to be plus x. Here I'm going to have plus 2x because, again, look at the coefficient in question. That means that at equilibrium, this is now going to have a concentration of x, and this is going to have a concentration of 2x. So when we go to solve for the KSP, what we're going to find is that at equilibrium, this is going to be x times 2x, and of course this is going to be squared. Now, here's where the most common trap occurs for students, and you have to make sure that you don't fall into this. If I had $1 for every time I've seen students tell me that this is going to equal therefore 4x squared, I would be rich. And the problem always comes in that everyone forgets that because it's 2x, we square that, and then we have to take into account the other x. When I do this correctly, I should say that in this case, we're going to have 1.4 times 10 to the negative 9th, and that's going to equal 4x, except it's going to be 4x cubed. So when everything is said and done and we solve for our value of x, in other words, when I take the cube root to solve for x, I get that x equals 7.04 times 10 to the negative 4th, which means then that at equilibrium, the concentration here is going to be 7.04 times 10 to the negative 4th. And so we're going to find is that at equilibrium, the concentration then for iodide is going to be 1.41 times 10 to the negative 3rd. So what do these equilibrium concentrations tell us? Well, it tells us that in order to ensure that the substance doesn't precipitate out, in other words, in order to make sure that the lead-2 iodide stays soluble, quote unquote, then we have to keep the concentrations of these two ions under the values that are presented here. And if you're looking at there and going, but wait, these are already teeny tiny values, you're right. If the concentration of lead ion gets too high or the concentration of iodide ion gets too high, then you will exceed the value of KSP. And if you exceed that value, then we've now produced too much ion in solution, and so some of it has to go back and it starts to bond together and thus becomes insoluble. Now, we have a special name for this value here, this 7.04 times 10 to the negative 4th. If you notice, the 7.04 times 10 to the negative 4th came from the change in x. Now, x, the value of x itself, represents this idea of the molar solubility. And the molar solubility, in a nutshell, is going to tell us to what extent does the solid ionize in water? To what extent does the solid disassociate or break up in water? And so the reason why we refer to this as molar solubility, and you see here I've written it as moles of solute divided by liters of solution, is because again, the solute wasn't the lead, the solute wasn't the iodide. The solute was the amount of PbI2. So in other words, the amount of the original salt that we found floating around in our solution. And so this idea of molar solubility is going to become critical because you will often be asked, what is the molar solubility of a particular substance? Or to what extent does that substance break up in water? So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.